So I'm going to be talking about the optimization of coating microstructure and mechanical properties for improved fracture resistance under repetitive impact loading. So coated components need to display high durability and wear resistance when subjected to interrupted contacts. So we've developed the nanoscale impact test, or the nano-impact test, as a rapid lab-based test to simulate these highly loaded contact conditions that occur when coatings are in service, particularly trying to simulate solid particulate erosion as occurs in jet engines, repetitive contacts in automotive engines in the valve train, and also high performance metal cutting applications such as interrupted turning and milling. So the Nano-impact test is one of the many test techniques in our NanoTest Vantage system, which is a modular nanomechanical, nanotribological test platform that comprises a range of different test techniques, indentation, scratch, impact, fretting, wear, across a range of different length scales by having a wide load range with 2 different loading heads, and also in different test environments such as hot or cold. So the red boxes show what I'm going to be talking about today. So how well does a mechanical property-based optimization work? So what are the limitations in using nano-indentation? So nano-indentation is a very versatile test technique, and it gives you information about the hardness and stiffness of coatings from a single test. So as Yitwar Chun has shown, although it's very popular to assume that H/E and H³/E² can be thought of as proxies for fracture toughness or hard coating systems, actually the real situation is a little bit more complicated than that, and they aren't direct measures of fracture toughness. So H/E is a measure of the elastic strain to break, and H³/E² is a measure of the resistance to plastic deformation, such that the critical load scales for plastic flow scales with the parameter in spherical indentation. So for a given applied load, contact is more likely to be elastic when H³/E² is increased. So it can also be thought of a little bit like a load carrying capacity parameter. So another very useful related index is the plasticity index for indentation, which is the plastic work done divided by the total work done. And this is sort of inversely correlated with this ratio of hardness to elastic modulus as shown in this equation here. And this, as Steve Fuller has shown, this plasticity index can correlate quite closely with erosion rate, in this case for a range of different bulk materials here, or some work from the Montreal group on the right showing how these 2 different indices, how the erosion rate is generally decreased for higher H³/E² and H/E. So in both of these 2 examples, minimizing plasticity in the coating systems has led to improved erosion resistance. So the question is this a general conclusion? Can we get everything from indentation? And in fact, the answer is no, that things can be a lot more complicated because you need to consider microstructure. So this is a very nice example from the aerospace industry. So in this case, in a jet engine, a TBC system to protect the superalloy from very high temperatures is subjected to particulate erosion, particularly in dusty environments. And this can lead to dimensional changes in the turbine blades, and this can decrease engine efficiency and even ultimately lead to engine failure. So this is an important area for Rolls-Royce, and they've been looking at this for some time. And in this example, they've been looking at the effect of thermal aging on the erosion performance of these different TBC systems. So in this, on the left, you can see the results from an erosion test, and the as received zirconia stabilized, yttria stabilized zirconia TBC has essentially got reasonable erosion resistance, but after thermal aging, the erosion resistance goes down. And you wouldn't predict that necessarily from the indentation test data. As you can see on the right, the thermal aging typically doubles the hardness, and yet nevertheless the erosion resistance decreases by more than a factor of 2 in these coating systems. So you're not able to predict the erosion performance from the mechanical properties in this example. Another example where you might assume different behavior than what you actually see is in metal cutting, in this case, in the end milling of a structural steel. So these are cutting test results for 2 different coatings of very similar stiffness to posted-on carbide. And this coating here is harder, and yet actually is a transition to a much faster wear regime, and coating failure really in quite a small amount of cutting. Whereas this coating here is a little bit softer, and yet it's much more damage tolerant. It extends for a lot longer before failing, and indeed you can run the test on longer. So again, it would be difficult to predict this based on mechanical properties. So we've taken a more direct approach, and we simulate these repetitive contacts with our nanoscale impact tests. So I'll introduce the test technique, and I'll give some examples on monolayered and multi-layered coatings, and show how we get some excellent correlations between coating behavior in the test and coating behavior in the actual field trial application. So indentation is a quasi-static test technique. So we get hardness and modulus, but we get that information at very low strain rates. In an impact test, if we are operating at much higher strain rates. And now we're getting dynamic information about the coating system. We can look at repetitive contacts and resistance to fracture failure. So it's a very useful technique for studying damage tolerance in hard ceramic thin films. And schematically, when these coating systems are subjected to impact, you get a complicated potentially complicated crack systems, as illustrated on the right. And you can imagine with multiple impacts, or in an erosion type test, these crack systems are going to coalesce, and this is going to lead to material removal. So we want to understand this and design our coating systems to mitigate these lateral fractures, essentially. So we do that with our nanoscale impact test, and we can think of it very much like a woodpecker tapping at a tree, and after a certain amount of tapping, then the material is removed. And it's a very tunable test. You can modify the probe material, the force of impact, the energy of impact, and the angle of impact. They can all be, and the time, number of impacts. These are all things that you can set. And the test is at very high strain rates, essentially, compared to indentation, which, as I showed, was typically something like 10 to the minus 2 per second. Here we are many orders of magnitude higher. So these are just a few repeats in this case on a bulk polycrystalline alumina sample being impacted with a sharp cube corner diamond indenter. And if we repetitively impact this same sample with this cube corner indenter, we can see one impact every 4 seconds. We can see a very small increase in depth until suddenly this impact here, there's an abrupt change in depth due to fracture of that coating system. And we can show that this is essentially due to a fracture event, because you've got this very nice massive burst of acoustic emission accompanying it. We can understand where the cracks are subsurface by doing focused ion beam cuts. As we move this red line through this impact crater, we can look at the cracking at different positions in this, under this impact crater, essentially. And we can see quite nicely that the cracks are following the grain boundaries in this sample. So in the TBC example, we want to simulate the erosion test with our impact test. And we do this by repetitively impacting on the top surface of the TBC and creating damage, leading to material removal under the tip. And when we do that, and we can do some really rapid tests. In this case, it's 1.5 minutes, so 3 minutes, sorry. And we get quite a nice correlation between the impact test data and the erosion data. And when you look with an SEM, you can see actually that it's sintering between the columns is what's causing this decrease in strain tolerance in the coating system, essentially. So reduction in porosity is meaning that impact events are able to travel over more columns now, and this is detrimental to its impact resistance and its erosion resistance. So we're quite nicely able to correlate between the impact and the erosion tests, although in general erosion mechanisms can be quite scale dependent. In this case, we're matching the contact length scale on the scale of the columns in both tests. Back to this metal cutting example, and we're able again to simulate this very nicely with our nanoscale impact test. In this case, just a minute and a half, and we see very, very similar behavior in both types of tests. So the fact that we can do repetitive tests rapidly allows us to screen many more coating compositions and to understand why and how these coating systems fail. And again, you wouldn't be able to easily predict this again from mechanical properties. You would probably assume that the titanium aluminum nitride coating would do better, but in fact, clearly it does not. So one of the ways to get more out of enhanced mechanical properties is to combine them with microstructural advantages. So one of the systems we've looked a lot at is nanolaminate systems. So they combine having high h cubed over e squared, which provides this additional load support and minimizes driving forces for crack formation, with additional routes for energy dissipation, which provide crack deflection along the interfaces, minimizing through thickness cracking. So that's very useful. And bending stresses are also important, as are high temperature properties. So we've looked at a range of different nano multi-layered coating systems and contrasted those with monolayered systems. And we looked on cemented carbide substrates and also hardened tool steels. So this first example is on cemented carbide. So a nano multi-layered titanium, aluminium, chromium, silicon, yttrium nitride nanolaminate with titanium, aluminium, chromium nitride system. So this retains some columnar structure, and it's a hard system. Its hardness is not so different from the monolayer coating systems it's being compared against. And yet when you look at its impact behavior and you look at its cutting behavior, you see a massive improvement in performance. So on the left, you can see it's particularly with 55% aluminium in these layers, you can see enhanced performance. It's a little bit of fracture, but basically very resistant through the test. And when you do the metal cutting test, you can see even right up to 700 meters per minute, so extremely high cutting speeds, it's able to deliver enhanced performance compared to to these monolayers. So really the combination of mechanical and microstructural advantages there in that system. So Alan Matthews has shown quite nicely that these multi-layers are subjecting to lower bending stresses. This is a very nice sort of macro scale example from about 20 years ago now, where he's just in a beam bending test, essentially at a certain strain level, the beam fractures. But when you compose this beam of, instead of a monolayer, but now of a multi-layered system, it's able to subject to much higher bending strains before it breaks, without breaking in this case. And you can see something similar in the cutting. So right at the cutting edge, you can see these individual layers are not fracturing, so they're subject to really high bending strains, and yet there's no fracture. So again, this is one of the reasons why these coating systems are so successful. Another example in this case, where the impact result is correlated quite nicely with the cutting tool life. So a low impact depth essentially means there's no fracture in the impact test, and that's correlating with the enhanced tool life, in this case for 4 different coatings. On cemented carbide. So these were all chemically the same, but the deposition was altered to create different amounts of interfaces in the coating system. So with a single layer deposition, then essentially there's nothing stopping these through thickness cracking through the system, and this is more susceptible to fracture. As you put more and more interfaces into that system, you enhance the fracture resistance. So there's additional routes for energy dissipation. You can see something similar here. In this case, this is contrasting a nanolaminate titanium aluminium silicon nitride system with a monolayered titanium nitride system, which is more columnar. And you can see now we've looked at impact tests over quite a wide range of different impact forces. And look, this is the final depth in the test. And at low load, you can see a really large advantage of having this enhanced h cubed over e squared in the material resisting this crack formation. Above a certain threshold, then you're getting fracture in both systems. But nevertheless, it's really providing a lot of advantages here in this system. And even at higher load, if you now do look at some focused iron beam, you can see there's much more spallation and fracture on the monolayer coating system. There's no interfacial failure, and that's because we've used very sharp cube corner indenters to concentrate the stresses within the coating. So we're really targeting the brittleness of the coating system here rather than, sorry, the coating rather than the entire coating substrate system. So if we're interested in looking at the entire coating substrate system, then we move more to micro scale impact testing. So we've developed micro impact tests. We've just adapted a similar approach for our high load head, and this allows us to produce more severe impacts with maximum forces, maximum energies, typically a couple of orders magnitude higher than is possible in nano impact. So it's, again, a very flexible test. It allows you to pull out almost an entire SN curve really rapidly. So you can set up matrices of tests at different loads and different amounts of, different number of impacts, different positions. And you can pull out very quickly the sort of information you see on the right there, where in this case it's showing a graded DLC having a better performance than some other DLC coating compositions over a range of loads. So by allowing greater energies, we can switch probe geometries. That allows us to understand and position the maximum stresses at interfaces, and we can look and investigate whether we've got any weak interfaces in the coating system. So we've done that, for example, in silicon doped DLC, and we've highlighted interfacial problems in these coating systems here, as you can see with the EDX, that the chromium and tungsten sublayers are clearly showing up after these impact tests. So we now look at essentially a monolayer titanium aluminium silicon nitride and a nanolaminate system, both deposited on cemented carbide in this case with slightly higher cobalt fraction. And these are the very hard systems now, and the nano multi-layered system is a little bit harder and a little bit higher, h cubed over e squared, not too much, but it still translates into enhanced performance at low load. So it's resistant to lateral fracture. So we do 75 impact tests, and you can see there's no lateral fracture at 1 Newton, and little tiny bit of ring cracking, but nothing too severe. As you increase the force on both coating systems, there's a transition to impact damage and lateral fracture outside of the impact crater. And particularly with a nano multi-layer system, that zone of lateral cracking is extending further. So again, you can think about, instead of the cracking driving towards interfacial failures through thickness cracking, then the stresses are going more perpendicular through the coating system. So the last thing I want to talk about is a little bit about high temperature nano and microscale impact testing. So if we think in general about how we design coatings for wear resistance, we often want to combine hardness and toughness, as shown in this excellent schematic from Sam Zhang, developing hard yet tough coating systems. But actually, if we think about many of these applications that we're trying to simulate, there's very high frictional temperatures involved generated in contact. So really, we're probably more interested in the high temperature properties of the coatings, the high temperature hardness, the high temperature toughness. So if we look at the at room temperature now, an impact crater at 1.5 newtons on this nano multi-layered system, you can see, as you can see, there's a large fracture zone. As we increase the temperature, we get a transition towards more plasticity-dominated deformation and less fracture, more plasticity. And this is down in this coating system primarily to enhance softening of the substrate underneath, because the coating system itself is actually retains some really quite high hardness up to 600 degrees. But the high cobalt fraction in the substrate leads to enhanced softening. If we want to look at the coating itself and we're less interested in the substrate, then we might switch to a nano-impact test. So we've done some high temperature nano-impact tests now at 500 degrees on titanium aluminium nitride coating systems, where we're varying that aluminium fraction between 0.5 and 0.67. And when we vary that, then we alter the fracture probability at room temperature. We alter the fracture probability at high temperature. The fracture probability at high temperature, again, it decreases, so it's improved resistance to fracture. And you can also see, again, that the aluminium titanium nitride coating system has enhanced resistance to fracture compared to the titanium aluminium nitride at these high temperatures as well. 500 degrees is not as high as the temperatures developed during continuous turning applications as shown here, but we're not trying to simulate those. We're trying to simulate interrupted cutting conditions where the test temperatures are typically a lot lower. And because we've got a close match on the repetitive contact, we've got a close match on the temperature, we get quite a nice correlation. So the enhanced behavior we see in our test actually correlates with what we see in many different metal cutting applications. In this case, having 67% AL in that coating system leads to enhanced tool life in a range of different milling applications. So hopefully I've shown how this nano impact test and these micro impact tests have a lot of potential for simulating interrupted contacts. And there's very, very close correlation between results in the rapid impact tests and the actual field trials of coating performance. And in optimizing coatings for these demanding applications, we really need to consider mechanical properties and the microstructure and how these work together to control resistance rather than think about these things in isolation. So coating design to increase the hardness modulus ratio is generally beneficial because it enhances resistance to plastic deformation, reduces coating bending and driving forces for crack formation. But it doesn't necessarily do much in terms of crack propagation. So therefore you need to combine that with multi-layer advantages. So nanolaminate structures particularly are useful at higher load in allowing crack deflection along these interfaces to relieve this strain accumulation. And by testing it across a range of different length scales and a range of different temperatures, we can really understand, I didn't talk so much about modeling, but we can also model these stress distributions. So we can really start to understand the entire coating substrate system and how this correlates with performance. So I'd like to thank, as well as the co-authors, all those people listed there. And if you're interested in further information, please see our website or drop me a line on the email shown there.